Rex, the giant carnivore of the Cretaceous period, 65 million years ago. The most fearsome predator of all time.
Tyrannosaurus Rex is an amazing animal, a little version of Godzilla.
T-Rex, its footsteps shook the earth.
It was an animal that, full grown, was about 40 feet long. It weighed 12,000 pounds.
Everybody knows all about T-Rex, right? Well, think again. Today, scientists are rewriting the script on T-Rex, using a trove of new finds, digging deep into the fossil record, and experimenting with new techniques. Scientists are forming a radically new image of T-Rex.
Looking at Tyrannosaurus Rex, it's more than just a big, powerful brute. It's an animal that was one of the last dinosaurs and one of the most sophisticated dinosaurs.
T-Rex? I would love to see an animal that big walking around on two legs. That would be a cool animal to see.
A new crew of paleontologists has arrived on the scene, and old assumptions are giving way to new hard facts. What have they learned? How are today's paleontologists revealing a new T-Rex? Only they can tell us. "65 million years ago, in a time period called the Cretaceous, lived Tyrannosaurus Rex, one of the largest carnivorous predators to ever walk the earth." Paleontologists have been certain of some basic facts about T-Rex for years. Its 40-foot length, 5-foot skull, 6-inch serrated teeth, tiny forearms, and colossal weight. At first, paleontologists thought T-Rex was a vicious loner, slow-moving and upright, dragging its massive tail on the ground. But everything we knew about T-Rex came from a handful of fragmentary fossils pieced together with limited scientific tools. Until now.
What we're seeing, I think, is a new breakthrough in interdisciplinary research. So taking aspects of traditional paleontology, engineering, biomechanics, and merging them all together, really.
High-tech science is revealing how to sex a T-Rex, how quickly it grew, how fast it moved, how it survived, and more. Modern research techniques, combined with an explosion of new fossil finds, 15 new specimens of T-Rex in the last 10 years alone, have led to a completely new understanding of Tyrannosaurus Rex and to a revolution in paleontology.
It's really neat to see how much has changed, because my very first meeting in 1993 was, probably the same as meetings had been for the previous 100 years. And now you go and you get a little bit of everything from molecular stuff to, just everything. It's really cool.
We thought we knew T-Rex, but we were wrong. This is the ultimate up-to-date guide to the cutting-edge science, which is creating a new T-Rex.
For years and years, people have sort of preconceived ideas of what dinosaurs were like as living animals. And they are preconceived. I mean, in order to figure out what an animal was like as a living creature, you actually have to study them.
Jack Horner has spearheaded many advances in the field of dinosaur research. In the last 10 years alone, Horner has discovered 8 specimens of T-Rex. Yet, his greatest contribution to paleontology has been perhaps as an iconoclastic teacher and thinker. Forever questioning, Horner has inspired a new generation of paleontologists who are reshaping our understanding of T-Rex from the ground up. In 1990, a new fossil was discovered that turned out to be the most intact T-Rex ever found. Her name was Sue, and at over 20 feet tall and 40 feet long, she is the world's largest Tyrannosaurus Rex. Until recently, little has been known about how T-Rex managed to grow so big or how long it lived. Greg Erickson, a former student of Jack Horner's, has been studying the growth and life cycle of T-Rex and has, in the process, found some of his basic assumptions challenged.
I expected this animal to have lived, maybe 60 years or something like that, very much like an elephant, which is the same size.
To find out if this was true for Sue, Erickson needed to determine how old she was when she died. Usually, paleontologists age dinosaurs by counting growth rings in the weight-bearing leg bones, just like counting the growth rings on a tree stump. But Erickson couldn't do this with Sue.
When I first started in dinosaur paleontology, I was told that it's not possible to figure out how old Tyrannosaurus Rex was or to figure out its growth rates. And the problem being is that people that try to age dinosaurs typically cut open the femur or the thigh bone and count the growth rings there. The problem that you have with an animal such as Tyrannosaurus Rex is that the bones are extremely hollow.
Then, Erickson made an unexpected discovery while examining tiny pieces of Sue's bones.
I noticed that some of the pieces that didn't go into the mount were actually quite solid, particularly the ribs and some of these hip bones, and also a bone called the fibula, which is one of the shin bones. And when I was looking at these under a dissecting microscope, I noticed that growth lines could be found stemming from the center all the way to the outside. So this suggested to me that it would be possible to actually age this dinosaur and probably other tyrannosaurs using those particular bones.
In order to test his theory that these were in fact growth rings, Erickson examined the rib bones of the closest known living relative of T-Rex, the American alligator, and found they too have growth rings. By matching the known ages of the gators with the number of rings in their rib bones, he discovered that they were genuine growth rings.
What this told me is that these alternative bones were very efficacious for aging reptiles and should work just fine at the aging of Tyrannosaurus Rex.
Erickson then examined the remains of 20 other tyrannosaurs of different ages and sizes, including 7 T-Rexes. Most of the tyrannosaurs he studied were in their teens. Sue, he found, was not only the biggest, but also the oldest known T-Rex.
Here you have this gigantic animal, but it lived less than 30 years. I mean, Sue died in its 29th year of life.
But the growth rings did more than just show how long a T-Rex could live. They would help Erickson answer another nagging question. How fast did these massive meat eaters grow? To do this, Erickson began by creating growth curves for T-Rex by charting out the age and weight of every Tyrannosaurus specimen he could find.
From the growth curve, you can figure out how long it took to reach adult size. Now, if you do this for Tyrannosaurus Rex and its closest relatives, we can figure out how its growth differed from that of its ancestors and figure out essentially how it became a giant.
Just as in trees, narrow rings show a slow rate of growth, while wide rings show a quicker rate. By comparing the growth and weight of different specimens, Erickson was able to chart the ultimate growth spurt.
We found that during the teenage years of this animal, I mean literally the teenage years, from about 12 to 18 years of age, this animal was putting on about 5 pounds of body mass per day. It's just amazing. It's like the ultimate Atkins diet gone bad.
But by age 20, Sue had already lived 2/3 of her life.
I was absolutely stunned when I found that Sue had died in its 29th year of age. Here this animal was just incredibly beat up and had arthritis and the whole bit. It had a really rough life, and yet it was so young when it died. I mean, this led me to, liken Tyrannosaurs to being, the James Dean of dinosaurs. They lived fast and they died young.
If bones can tell us how long Sue lived, maybe they can tell us about her physical condition at the time of her death. Sue's bones were found riddled with trauma, including a fracture on the left leg, which may have crippled the massive animal. Elizabeth Riga, a paleopathologist, looks for evidence of disease and trauma in human and dinosaur remains. The clues she has found in Sue's bones have challenged our assumptions about the life and death of T. rex.
We've got an infection of the leg of the fibula that's very florid and well healed, and that's really critical, I think, in understanding all of Sue's pathologies. We've got a number of rib fractures, one of which is non-united, so it's still broken. It didn't heal properly. And then, of course, some of the pathologies that have been most intriguing to people, which have been these multiple asymmetric sort of healed lesions of primarily the post-dentary bones.
These holes at the back of Sue's jaw have been a mystery to paleontologists. Some assume they were from the bite of another T. rex and ultimately may have killed her. Using her expertise in pathology, Dr. Riga was able to reinterpret the origin of these cavities.
They do at first blush look a little bit like they could be bite marks, but there are a number of things I think that argue against that. One is the pattern. They don't really line up with teeth. So if they were bites, you would expect that all of the holes would be parallel to each other, as if you're having a strike and a pull. Secondly, they're in an area that is, if you think about it, really, really hard to bite. These are back here at the back corner of the jaw. That's a really difficult place to try to even place a bite.
So, if they aren't bite marks, what are they? Elizabeth Riga believes she has found the answer by looking at bacteria in living animals.
If you're looking at an organism like actinomyces, which is an anaerobic organism, it's a natural mouth flora in many organisms, such as cattle. It's also found in wallabies and kangaroos. Those lesions tend to restrict themselves a little bit more posteriorly, and they cause lesions that are virtually identical morphologically to the lesions that we find in Sue. So an animal apparently riddled with pathology, and yet I would maintain a healthy animal.
Even riddled with infection, Riga is impressed with Sue's resilience. Injury, infection, and disease are a part of life. Either an animal succumbs to illness or its immune system battles back, indicating a hale and hardy animal like Sue.
It would be akin to an athlete suffering injuries. You know, that person is arguably extremely healthy and is still going to be suffering injuries because of doing things that really push the envelope athletically.
Maybe Sue was the Michael Jordan of dinosaurs, dominating the court even with a battery of injuries. Although we still don't know exactly why T. rex had such a short lifespan, Elizabeth Riga's research indicates that, while alive, T. rex successfully fought internal as well as external battles. Until recently, paleontologists speculated that Tyrannosaurus Rex was a speedster, able to run over 35 miles per hour. New research is telling us otherwise. T. rex, a bipedal animal with tiny arms and a 15-foot tail, had to balance out a lot of weight to get moving. How did this work, and how did the size of T. rex's skeleton and muscles determine its maximum running speed? Studying these questions at the Royal Veterinary College in London is John Hutchinson, a specialist in the evolution of anatomy and locomotion. Using foot-mounted accelerometers, GPS transmitters, and motion detectors, Hutchinson has turned to the world's largest land animal, the elephant, to understand the biomechanics of mass, weight, and motion in relation to T. rex.
Elephants really are quite peculiar as animals go, and probably don't tell us as much as some might assume they would about a T. rex. However, they have some interesting parallels with dinosaurs. Unlike most other animals, they stand and move on very straight legs. Did dinosaurs do the same thing? Certainly some of them seem to have, but did T. rex, which was about the same size as an elephant, did it have to move on rather straight legs like an elephant, or did it have more possibilities for how it could have stood and moved?
The elephant spreads its massive bulk over 4 legs, whereas T. rex held all its weight with just 2 legs. But for Hutchinson, whether 2 legs or 4, the basic equation of moving a gigantic animal remains the same. How do bones and muscles work together to move such huge mass efficiently?
Putting the mass of an elephant on two legs kind of raises a whole other question for T-Rex. Could it even behave as athletically as an elephant? I suspect it was probably a bit more athletic than an elephant, but it's a difficult question, and to really address it with a T-Rex, for example, we first need to understand how big animals work today.
The data gathered by the different sensors attached to the elephants allows Hutchinson to reconstruct how the forces of mass and gravity affect the acceleration and velocity of the elephants as they move. Hutchinson has found that the underlying physical principles that determine the speed of both T-Rex and elephants are the same. Too much muscle and they are constrained by gravity. Too little and they can't lift their bones.
Their muscles can't produce enough force. They just can't do very athletic things. And that's something I've applied then to T-Rex. In some of my early work, I tried to calculate how large the leg muscles of a T-Rex would need to be for it to run at over 25 miles an hour. And that carried with it the implicit assumption that the force that muscles can produce, which is directly related to their mass, is a limiting factor in achieving a certain speed.
Hutchinson calculated that T-Rex ran much slower than previously thought, not 35, but more like 15 to 20 miles per hour. A ground-shaking, though stately pace, which still allowed it to reach the escape velocity of its favored prey, huge herbivores that were also limited in speed by their incredible weight. Taking his work from the field into the lab, Hutchinson is using computer models to reconstruct how T-Rex might have walked and what its posture would have been. Clues are found in the attachment sites of muscles, acting like telltale fingerprints on the bones.
What we've been looking at so far is trying to tease apart how straight-legged could it be versus how crouched could its legs be and still be functional for walking and running. Crouch position, no matter what your size is, it takes more muscle activity, just more energy really to sustain that kind of a posture.
When you're as big as T-Rex, you have to struggle against a lot of different forces. To maintain its balance and maneuverability, Hutchinson believes that T-Rex had to be a lot more straight-legged and slower than previously thought.
I think what made T-Rex amazing, if we were to see it, is that it was so different from living things today. It was a blend of old features that crocodiles still have today and new features that birds took and elaborated even further. So it's kind of a chimera, a mix of old and new and weird features. That's what makes it an interesting scientific question, because how does a 6-7 ton animal stand and move on two legs, and how could it move anything like a bird if it had that huge tail and other different proportions of its anatomy? It had to be different, but how different is a cool question.
New research has provided scientists with insights to the physiology of T-Rex. But what about its behavior? How can we hope to learn anything when all that has survived after 65 million years are bones? The bone bed that held Sue also contained the remains of several T-Rexes, including a juvenile. This bed, and others in Canada and Montana, have started paleontologists thinking about T-Rex's social life. Was T-Rex really a solitary hunter as we've always believed? Phil Curry has found evidence to challenge that view.
Tyrannosaurs were almost certainly social animals. We can get that from looking at the Albertosaurus bone bed or the Sioux quarry, where we had parts of 4 skeletons in the same place at the same time. And they all died at once, and again suggesting that these animals did travel in social groups.
One Tyrannosaurus is frightening enough. So why would they have needed to travel in packs?
fact that you have everything from very small animals to very large animals suggests that they were, in fact, taking care of their young in a sense. So that's one line of evidence to suggest that they were sociable animals.
Curry believes T-Rex not only traveled together as a caretaking family unit, but they hunted together as well, employing a strategy similar to wolves today.
There was some kind of collective strategy involved in the hunt. And it does make some kind of sense that there would be, because we see that today with modern predators that travel in packs, and we know that it's especially important if what you're going after are animals that are moving in big herds. And we do know that duck-billed dinosaurs and ceratopsian dinosaurs tended to move in these gigantic herds of hundreds or thousands of animals, as presumably a strategy in part for protecting themselves against predators.
Scientists can only speculate how T-Rex operated as a social group, but the finding that different ages traveled together does suggest the plausibility of the T-Rex hunting pack theory. The image of T-Rex as a lone predator is giving way to an intergenerational group portrait of a highly social species, perhaps one with large brains. In an effort to gain a greater understanding of dinosaur fossils, paleontologists have borrowed high-tech tools from other disciplines. Overseeing a study of Sioux, the largest T-Rex ever found, was paleontologist Chris Brochu.
My job was to write a complete description, a monographic description of the skeleton of Sioux, inside and out, based on looking at the skeleton, based on comparisons with other theropod skeletons that I went and looked at, and based on the data set we got from the high-res computed tomographic analysis, from the CAT scanning, basically, of the skull. We generated a set of 748 slices. Each one is 2 millimeters thick, from the tip of the nose to the back of the skull.
CT scanning yielded a 360-degree image and cross-sectional views of the skull interior, like digital slices of a loaf of bread. Slice by slice, paleontologists were able to peer into the three-dimensional skull and determine the brain size of T-Rex, believed to be approximately a foot long and filling the same volume as a quart of milk.
One of the neat things about Tyrannosaurus Rex and the tyrannosaurs is, they don't have big brains. I mean, if you look at the brain of T-Rex, it's about that long. Well, that's pretty good next to us, but it's only about this thick. So it's not overly impressive, but obviously it was impressive enough for its time. And an important aspect of brain size is not how big your brain is, but how you use it, of course.
Studying the skull architecture has revealed never-before-seen clues as to how T-Rex's senses functioned.
The olfactory bulbs were large. Whether that indicates an overly acute sense of smell is unknown, but certainly they did have a robust sense of smell.
With the eyes, we know that the optic lobes were well enough developed. We had large eyes in Tyrannosaurus Rex. There's a whole system of sinuses associated with the middle ear of Tyrannosaurus that suggests that it probably was a very good hearer as well.
The full range of senses that a large meat-eating, possibly predatory animal should have were all there. Whether T-Rex focused on smell over sight is very difficult to say.
CT scans allowed scientists to get inside the brain cavity of T-Rex. Other innovative technologies are breaking apart our expectations of what secrets fossils might hold. In 2005, paleontologist Jack Horner was forced to break the leg of a recently excavated Tyrannosaurus in order to get it on a helicopter. Horner sent parts of the bone to his former student, Mary Higby Schweitzer, who studies the microstructure of bones.
And I picked out one piece and I looked at it and I said, oh my gosh, it's a girl and it's pregnant.
Schweitzer was able to identify special bone tissue called medullary bone tissue, similar to that formed in female birds when they are getting ready to lay eggs. For the first time, scientists were able to sex a T-Rex.
the tissue is very apparent. It's very distinct, it's very apparent, and I have done a lot of studies on physiology, bird physiology actually, and so I knew immediately what it was.
To corroborate the finding, Schweitzer and her lab tech, Jennifer Whitmire, looked within the bones of the most primitive living birds, the flightless giants, emus and ostriches. Incredibly, they found the very same kind of tissue.
They're highly vascular, they're woven bone pattern, they contain deep sinuses for fast mobilization of calcium, and all of those features are consistent with the T-Rex. So those are features found distributed throughout modern taxa and in our dinosaur.
Then, using a technique unusual for paleontology, Schweitzer's assistant demineralized the bone. As she looked for more evidence of medullary tissue, she found another surprise.
She came to me and she said, "You're not going to believe this, but it stretches. It stretches when I pick it up." As soon as the minerals were removed, it started acting like modern bone. And it was sort of like a scene out of the Twilight Zone. I kind of felt like, this is not possible. I'm seeing something that's not possible.
It seemed impossible, but for the first time ever, Schweitzer was able to extract and study soft tissue containing blood vessels and cell nuclei from a 70-million-year-old fossil.
We realized that this bone, this medullary bone, was preserved in such a way that something remained when we removed the minerals, and that's not supposed to happen with dinosaurs. And so it's the process of removing the mineral that lets you see what else is left. And most people don't like to dissolve away dinosaurs, so nobody really does this, but I do. So I kind of was trained to destroy things, so it comes very naturally.
Now, it's impossible for paleontologists to look at old bones the same way again. What other secrets are still waiting to be discovered? What other tools and techniques have yet to be tried to recover the past? Paleontologists have always known that Tyrannosaurus Rex had a gargantuan head and mouth. But they didn't know much in detail about how it worked as the animal's major tool in gathering food. Now, scientists have the tools to ask, just how bad was T-Rex's bite? Biologist Greg Erickson thinks he knows. When not in the lab, Erickson is in the field wrangling gators. There, he has taken his two passions and fused them in a cutting-edge research program to test his theories about the bite of T-Rex.
Crocodilians are the only toothed archosaurian reptiles. In other words, they're close relatives of the group that dinosaurs belong to, but they're the only ones living that have teeth. So crocodilians are our best model to figure out how the teeth and the muscles and the jaws and all that worked biomechanically to allow these animals to generate bite forces.
In order to determine the bite force of a living alligator, Erickson uses a tool called a bite force transducer.
Basically what we do is you go up to an alligator and tap them on the snout and they'll open up. They're more than willing to bite you. And you stick this device on their teeth and they bite down on that and it registers the force instantly and we record that on our computers.
The data Erickson collects allows him to understand how everything from the tissue to the teeth to bones and muscle of an alligator function, enabling him to estimate what the actual bite force of T-Rex would have been.
It's all very preliminary at this point, but I suspect that the bite forces of Tyrannosaurus Rex were somewhere in the range of 20,000 pounds. Essentially cut right through you is what it would do. They wouldn't actually get a grip on you as much as they'd just take a huge chunk out of you.
A lot could be learned from seeing the actual effects of such bite force. But finding a fossil with the bite of a predator left on it is very rare. In the mountains of Montana, however, Ken Olson, a retired Lutheran minister, found a Triceratops skeleton, which he shared with Greg Erickson.
There was a portion of bone about 5 inches long that had weathered out. This would be the very, very far end of it. And We knew there was something special there because the one bite mark was evident at that very edge of the bone.
It looked like a giant dog had worked it over or something. It was unbelievable. And so that got me sort of started looking at how Tyrannosaurus Rex actually fed, and also looking at its physical capacities. In other words, how did it use that remarkable dentition, and what kind of forces were involved.
Greg Erickson began to examine the Triceratops skeleton like a forensic detective trying to figure out who done it.
One of the first things I looked at on the specimen were the size of the bite marks. I looked at the spacing between the teeth. Was it consistent with a Tyrannosaurus Rex or with a large crocodile? I looked for evidence of serrations. The backs of Tyrannosaurus teeth have little steak knife-like serrations, and so if we found those marks on the bones, it would be pretty compelling evidence that this was from a Tyrannosaur and not a crocodile.
Erickson took some dental putty and inserted it into the deep puncture marks.
When I pulled it out, lo and behold, I was holding replicas of the teeth of the animal that actually made these bite marks, and this was the spitting image of Tyrannosaurus Rex teeth, and that really kind of sealed the deal there.
Once Erickson confirmed the culprit, he was able to analyze the bite technique of T-Rex.
Clearly what had happened here is what we call puncture and pull feeding. What these animals did is they bit very forcefully into this poor hapless animal, and then it pulled backwards and essentially made these huge cuts right through the bone. It looked like a hot knife had cut through butter.
With this kind of deadly attack, T-Rex didn't need to use those strangely foreshortened forearms to subdue its prey. Its tremendous bite force and crafty technique rendered them obsolete. Delving further into the inner workings of T-Rex's jaw and skull is Emily Rayfield. Using finite element analysis, a technique borrowed from engineering, Rayfield is tracing the evolutionary adaptations in the T-Rex skull to accommodate such a powerful bite force.
I was interested in to see how far we could develop this technique to actually look at stress and strain within the skeletons of extinct animals and living animals as well too.
Using CT scans of Sioux, Rayfield constructed a digital 3D model of a T-Rex head for testing how bite force impacted the skull's skeletal structure when it was chomping down on its prey.
So what we do then is apply a bite force to specific points on the skull. In this instance, I've applied it to the edges of the teeth along here. And what we're seeing here is how the skull's deforming in response to a load, i.e. the bone is being pushed together. And this scale bar on the right-hand side shows, as you move down the scale, areas which are increasingly more green and blue have much higher areas of compressional stress there. So the bones are really being pushed together in those regions. So that turns out to be up here in the region of the nasal bones and up here as well above the eye.
Rayfield has found that the left and right upper parts of the nasal bone of T-Rex are fused together. She believes that this adaptation in the structure of the T-Rex skull evolved to absorb the tremendous pressure of T-Rex's bite force. With her model, Rayfield was also intrigued to find that, just the opposite of the nasal bones, many of the jaw bones in T-Rex are free-floating, not fused.
Now, to me, this seems paradoxical in the sense that on the one hand you've got an animal which is creating a very powerful bite, chomping through bone, but it's got these openings which remain open in its skull. So perhaps what's going on here is that those bones stay open, so soft tissues that bind them together can act as shock absorbers when the animal's biting.
Rayfield's computer model has enabled her to deduce the importance of bite force in the evolution of the unique shape of T-Rex's skull. With Emily Rayfield and Greg Erickson's research, scientists now have a sophisticated way of quantifying and analyzing the deadly force of T-Rex as it came to dominate the Cretaceous world. For most of the first 100 years since their emergence as fossils, tyrannosaurs were seen as lizard-like. Then, a scientific revolution took place. Newly unearthed fossils have upended the very physical image of T. rex and its place in the prehistoric animal kingdom, connecting the story of T. rex to the other major revolution in dinosaur biology: the origin of birds. In 2004, Mark Norell of the American Museum of Natural History and Chinese paleontologist Xu Xing discovered a small tyrannosaur in the famous paper shales of China's Liaoning province. These fossil beds are made up of paper-thin layers of volcanic ash, so finely grained that they preserve even the softest and most delicate features of plants and animals. One of the creatures caught there is one of the earliest known members of the Tyrannosaur family, Dilong paradoxus.
Actually, the first time I saw the first specimen was several years ago, and it was just a very fragmentary specimen. And we knew it was something interesting, we just didn't know how important that it would be when we found one which was much more complete, and from that we could determine it was a Tyrannosaur.
Dilong was only 5 feet long, but was undeniably a Tyrannosaur, confirmed by several findings.
Well, we can tell that Dilong is a Tyrannosaur just because it has a lot of attributes that Tyrannosaurs have. I mean, for instance, the teeth at the front of the mouth are D-shaped in cross-section, which is a characteristic which is only found in Tyrannosaurs.
It had one characteristic, however, that few would have guessed. Upon close inspection, the fuzzy imprints surrounding the fossil skull and tail revealed the distinctive branch structure of feathers. A number of other recent fossil discoveries from Liaoning have confirmed that feathers evolved in theropod dinosaurs before the appearance of birds or the origin of flight. Small, fast-moving theropods like Microraptor were found fossilized with feathers.
We have so many animals that are closely related to T. rex and Dilong that have feathers, and we have evidence that Dilong has at least primitive feathers. We would predict that the common ancestor of Tyrannosaurus Rex and Dilong was also a fluffy, feathered creature. So we would then predict that T. rex, at least at some stage of its life, when it was small perhaps, would have been a feathery animal also.
Research shows that the stages in which modern feathers grow mirror their evolutionary history. At their earliest stage of development, feathers are simple, hollow, tubular structures or downy tufts, like the fuzz on Dilong. These feathers probably acted as insulation, an essential function of feathers to this day. Therefore, it shouldn't surprise us to see a newborn T. rex as downy as a little chick. Just as we've begun to get comfortable with all the new findings, an unexpected twist in the story of T. rex appears. Another recent find in China has placed a new node on the dinosaur family tree. In 2005, Xu Xing and paleontologist James Clark unearthed a fossil named Guanlong Wu Kai, a small, 10-foot creature believed to be yet another direct ancestor of T. rex and the oldest tyrannosaur ever found.
This is 160 million-year-old deposits, and Tyrannosaurus Rex is about 65 million years old. So, you know, this is a long time before Tyrannosaurus Rex. This is almost 100 million years older, and T. rex is only 65 million years older than us. So there's more time between T. rex and Guanlong than there was after T. rex to us. So what it's telling us is they go back a long ways, and you know, there are things out there that we haven't discovered yet. There must be other early tyrannosaurs out there.
But were all ancestors of T. rex small like the 5-foot Dilong and the 10-foot Guanlong? The fact that T. rex grew so large led scientists, since its initial discovery, to classify T. rex as a carnosaur, a family of theropods whose members include many other giant dinosaurs. The discovery of Guanlong, however, shed new light on the evolutionary history of T. rex.
There has been this question. Basically, Tyrannosaurs, especially Tyrannosaurus, are very big, and there are a lot of features that are shared between Tyrannosaurus and some of the big carnivorous dinosaurs of the Jurassic, like Allosaurus. So people had thought that they were related, that Allosaurus and Tyrannosaurus were a group called the Carnosaurs.
But size alone does not determine family origins. New fossil finds like Guanlong, as well as specific parts of its anatomy, have led paleontologists to realize that T. rex actually belongs to another branch of theropods, the Coelurosaurs. The Carnosaur and Coelurosaur families evolved at different times from small creatures into two independent lineages of gigantic meat-eating predators. Aided by remarkable fossils like Guanlong, scientists have been able to demonstrate that T. rex and the other Coelurosaurs are more closely related than the Carnosaurs to creatures in our very midst today. In fact, paleontologists and ornithologists have both recently concluded that birds evolved from the same group of bipedal meat-eating dinosaurs that includes tyrannosaurs, thus confirming the shared evolutionary path of T. rex and modern living birds. Could this, by chance, explain an unusual body part found on Guanlong?
The first thing you would notice about Guanlong is that it had a crest on the top of its head. And it's the only tyrannosaur with a crest on the top of its head.
What purpose did the crest serve? Clark has a hunch.
The crest was probably a display structure because the living animals that have crests generally use them as display structures. And so either they're signaling to other members of their species that they are a member of that species, or they're signaling to things that are not that species, beware of me or stay away from me.
An example would be the cassowary of Australia. Who knew? T. rex is one of its distant cousins. New science has revised our conception of the most iconic dinosaur, Tyrannosaurus Rex. The recent flood of fossil discoveries, combined with the latest advances in forensic techniques, have revealed a more nuanced, complex portrait of this prehistoric giant than ever before.
And I think that what we're finding is that the fossil record is capable of a lot more than we thought it would be.
T. rex has been transformed from a skeletal impression to a three-dimensional creature. From its earliest origins to the height of its power, we now understand T. rex as never before.
Approach is everything. If you are locked into this idea that you're not going to find something and you don't look for it, then you'll never find it. Even a dry old Tyrannosaurus Rex bone, if you look at it the right way and then take notice of what you're seeing, maybe you're going to get a big surprise.
No matter what is learned, T. rex, who reigned on Earth longer than any other creature, will always be king or queen.